have got the second flow of our instructions and guidelines, and that's concerning the infinitesimal analysis course. So here we are at the integration. So the first thing we shall deal with is the so-called definite integral. And that's nothing but the reverse procedure to differentiation. So you see, we are having a function f, and we want to find whether this function is a derivative of some other function, big F, capital F. In terms of differentials, it's easy to write it down. So the differential of the capital F should be fx dx. And that's called the primitive function or indefinite integral, and in English literature also quite often antiderivative. And traditionally we write that the capital F is the integral of the lowercase f. And of course the x is the same on both sides in this case, but we shall come back to this later. And a simple observation is that the primitive function is sort of nearly well defined if it exists, because it's defined at each interval uniquely up to an additive constant. And this is easy to see, because if you have two such primitive functions, that their difference will have derivative 0 all over the interval AB. And by the mean value theorem we know that then the values on the beginning and the end must be the same, and so the whole functions f and g are different by constant only. So that's straightforward, we don't have to go into detail, but therefore we mostly write the indefinite interval as something which has got a unknown constant c there. If we have a complex valued real function f, then of course the primitive functions, the antiderivatives, makes completely sense, no problem with that. And we know that the derivatives are computed component wise, so also the antiderivatives will be found component wise. So without lots of generality we can just restrict ourselves now to the real value, the real functions. So that's very straightforward. Now let's add some, say, intuitive justification why the Newton integral should be, so the looking for antiderivative should be considered as a good tool for something we are after. And what we are after is actually, we have got the x, we have got the y equals some fx, and we imagine that you have got something like this on an interval AB. So what we really want to do is we have something like the area below the graph, and we think that the values of f, so if I have the values, so you see, so I'm adding something like the contribution to the area, which is just this small piece, and infinitesimally it's only the line, but in reality it will be, if I split the interval, if I split it to several subintervals like that, so that will be x0, here are the xi's, this is xn, the b, then I can always see the small f as the derivative of the capital F. And we know that, well, if we take the forward difference for the derivative, then it means we have to compute the derivative approximately as the difference of the value divided by the difference of the arguments. And so if I would, instead of thinking infinitesimally, think this way, so this is this xi plus 2 or I plus 1, here is the xi, then what I do is I compute the estimate for the area in such a way that it will be just the fix here times the width, right? So I simply approximate the value of the function along this subinterval by the unique value fxi. And then you see I have to add these particular n intervals. These two guys cancel each other, and what I end with, so that's a telescopic sum, so it's always just added and subtracted, except the first one, which is fa, and the last one fb. And therefore you see that if I have found a antiderivative, then it's very good idea to believe that in some sense the area below the graph is defined as fb minus fa. Let us notice that we haven't defined what the area is yet. So this might be simply our definition of the area, and then we would think about what are the properties of such a concept. Well, we shall proceed slightly different way in the future, but for now this is a good result. This is a good reason why to define the definite interval in the style of Newton, which will be simply the difference of the boundary values of the capital F function, the antiderivative. And you see that the antiderivative is defined uniquely up to a constant, and because you have the difference, the constants disappears. So this is uniquely defined, right? So if there is a antiderivative to small f, then the Newton definite integral with bounds on the interval with bounds a and b is well defined. Right, so this is the definition. So now, what is such a definition good for? So first of all, we can, of course, consider the fact that it's nothing but a reverse procedure to derivative, and so whenever we have a list of derivatives, we can read it the other way around as a list of the primitive functions. So this is what we've got here. So simply differentiating the guys on the right hand side will give you the guys inside of the integrals, and so this is a well arranged table of some examples of indefinite integrals. Moreover, of course, you can imagine that for example, if we have got a integrand of this form, then of course this will always be having the antiderivative of this kind and so on, right? So there are some rules, but there are some smarter rules which come in a very straightforward and easy way from the rules for derivatives. We just have to reverse the rules. So there is the Leibniz rule for derivative of products, right? And you know that it's just a sum of two terms. In each of them we differentiate one of the functions and multiply with the other. And this is leading to what we call integration by parts. So you simply know that by the very definition of the antiderivative and by the very Leibniz rule, we simply get this. Right? And this is useful if we can compute the function g from knowing the g dash. So it means if we know the antiderivative to g, and if this integral is easier to compute than the left hand side one. Or it might be also appearing in recurrences. So simply we do that procedure several times and we come back to the original integral after a few tries of applying the rule, and then it gives us some recurrence relation which allows us to compute the integral itself. So there are examples here showing how it works. So for example, if you have x times sine x, then it's easy to choose. So f would be x, and we know antiderivative of sine is minus cosine, and therefore we immediately get the result, right? So that's very easy going. Similarly, it's quite useful sometimes to consider 1 as the g dash, and then you can, for example, compute what's the antiderivative of logarithm, right? Without this trick would be difficult, but with this trick it's easy, because you see immediately that it's this minus 1 over x. The x's just cancel each other, so you see it's just an easy way. The other standard rule is the chain rule, so how we differentiate composition of functions, and that's again it's here. So we write it with differential, so the dx would go to the right hand side, and you immediately see the result of this is the so-called substitution, right? And this is what people call integration by substitution. Of course, if you do it for the indefinite integral, then you have to revert the substitution in the end to write down the antiderivative explicitly, but usually this is used for computing the the finite integrals, and there you simply recompute the bounds, right, following the substitution. So that's something very straightforward. You will easily find it yourself. Here is what I mentioned already. So for example, if you want to compute the antiderivative to the m's power of cosine, then you do the integration by parts twice, and you get this recurrence, right? So, and the initial values are computed easily, so out of that you can then compute any im with finite m, right? So it's not straightforward, because it's just needing, but you need just, it won't be a simple formula, but it's possible, right? Similarly, say, so you have got these kind of integrals. So there are some examples, as you see. And the last thing, how to find the antiderivatives, the primitive integrals, is an approach which makes it absolutely easygoing and discrete if you are to integrate a rational function, right? So this is one of the elements in our zoo. So for example, this is a rational function of a very simple kind, and you immediately see the solution, right? So you also can integrate all these ones, because it's just a power function. And now, if you have something more complicated like this guy, it turns out that you always can write such a thing as a sum of terms which are of the previous kind or slightly different, right? So for example, in this particular example, we immediately can integrate the seemingly complicated thing in this easy measure. And this is called the decomposition in partial fractions. It's a purely algebraic procedure, belongs rather to combinatorics than anywhere else, and it's just simply going with the fact that if you are able to decompose the denominator polynomial into root factors, then you can, if they are all with multiplicity 1, you can write it in this way, always. If they are with higher multiplicities, it makes the life more difficult, and you can read through here how it works. I will not go through the details in these guidelines, because it just, you see, so if there is a multiple root and it's just real, then you can see that it would give you the partial fractions of this kind, which is all fine. If there would be a complex if there would be complex roots, so you would have some factors in the decomposition of the denominator polynomial of this kind, and the powers of those, then you again can find them in this way. And there are ways how to compute all the polynomials. So therefore, whenever you would ask, say, Sage or Maple or whichever of these computer-aided mathematics software to integrate this kind of rational functions, it will always give you a nice answer. No worries, no problems. So I think that's it for the Newton integration approach.